Welcome to our first video on Chapter 4 from our Zane State Physics class, where we are looking at dynamics. Now, in the last chapter, we looked at kinematics, which is basically studying the way objects move. And now we're looking at dynamics, which is essentially why they move the way they do. So we're going to be looking at forces and Newton's laws of motion. So what is a force? A force is basically a push or a pull on an object. It tends to cause motion, and it is required to change the velocity of a moving object. So here in the image we have a girl pushing a cartload of watermelons, and in the image below that, the hand is pulling on this box with a force that is causing it to slide along the table. Now, a force doesn't always cause an object to move. It could just simply cause internal stresses, and we'll talk about that type of mechanics of materials in a later chapter. But for the most part, we're going to be looking in this chapter at forces on objects that are free to move. So Newton, Isaac Newton, very famous scientist, you've probably heard of, has developed several laws of motion. The first of which is the law of inertia, and you've probably heard this before. It's pretty commonly known. It's often stated along the lines of an object at rest tends to stay at rest, and an object in motion tends to stay in motion. And that is true unless an outside force acts on it. So an object will not spontaneously move without some force being present, like our couch potato here. And the air hockey table is a pretty good example, pretty good approximation of a frictionless surface. Friction is something that does sort of complicate these models and these ideas of motion going on indefinitely, because friction slows objects down and brings them to a stop. But in the absence of friction, an object in motion, if you were to hit the air hockey puck and it could travel on a bed of air, an air hockey table that was infinitely long, it would just continue to move at the same velocity in the same direction forever until some other force acts on it. So in reality, when it comes to a stop, that's because there is a force acting on it, and that force is friction, or air resistance, or a collision with some other object. And those will either cause the motion to stop or change its direction. Another thing we need to consider when talking about forces is mass. So mass is essentially how much stuff there is in an object, what it's made of, how much of it there is. So the more mass an object has, the more inertia it has, the greater force is required to move it or change its direction if it's already in motion. In the metric system, the unit of mass that we use is the kilogram. Gram is technically the base unit, but because the gram is so small and most objects we deal with are considerably larger, we use kilograms as our standard unit. Now, it is important to draw a distinction between mass and weight. And I mentioned this in an earlier video, but it bears repeating. Mass is not the same thing as weight. Mass remains constant regardless of the situation. If you have a bowling ball that has a certain amount of mass, Doesn't matter if it's on Earth, on the Moon, on Jupiter, in outer space, at the top of Mount Everest, or the bottom of Death Valley. It still has the same amount of mass. Its weight, however, will change with all of those situations because weight is the force exerted on an object by gravity. And we'll talk in a later chapter more about gravity, but we're all pretty familiar with the fact that gravity pulls everything down towards the center of the Earth. And the more mass something has, the more weight it has. So they're very closely related, but they're not exactly the same thing. Because if you were to go to the moon, you would have less weight because the moon has less gravitational acceleration. It's about 1/6. So you'd only have about 1/6 of the weight on the moon. You would have much more weight on Jupiter. You would have more weight at the bottom of Death Valley than you would at the top of Mount Everest. And we'll talk in a later chapter about why that is. So we use the metric system in this class, and oftentimes pounds and kilograms are treated as though they are units of the same type, but they're not, because pounds are a unit of force and kilograms are a unit of mass. So what is the British equivalent of a kilogram then, or what is the corresponding unit? What is the unit for mass? It's lesser known because it's not really used very much, but it is the slug. The British unit of mass is a slug. Newton's second law of motion is essentially, it can be written as this very brief formula here. So let me get my pen set up. There we go. So this equation right here is Newton's second law. And what this is saying is this is the Greek letter sigma. It's used to indicate a sum, adding things together. So this is saying the sum of forces, we've got F with a line over it indicating that force is a vector, it has both magnitude and direction, is equal to m, little m is mass, and a is acceleration. And a is, acceleration is also a vector quantity. It's got the arrow on top of it. So essentially Newton's second law of motion is just force equals mass times acceleration, or the sum of forces equals mass times acceleration, because oftentimes there are multiple forces acting on an object at once. So for instance, here we have these bobsledders. The three of them are applying a force to the bobsled, which is causing it to accelerate. So the sum of their three forces on the bobsled causes it to accelerate. This is a little science joke I like here. May the mass times acceleration be with you, because mass times acceleration is force. So just to recap, we have here Newton's second law, that the sum of forces equals mass times acceleration. The unit of force in the metric system is the Newton. Newton's pretty famous for his laws of motion involving forces, and so the unit of force is named after him. So we have the Newton. So as I was saying before, a kilogram is a unit of mass. Okay, kilogram here is mass. The British equivalent of that is a slug. And forces we have newtons and pounds. So we're all used to pounds when measuring weight. In the metric system, we have newtons. Now there's also a metric unit called a dyne, which is a gram times centimeter per second squared. But we're not going to really use that. We use the SI system, not the CGS, which is centimeters, grams, and seconds. We use meters, kilograms, and seconds, or that's the SI system. So Newton is a derived unit if force is equal to mass times acceleration, and mass is kilograms, and acceleration is meters per second squared, then we end up with a kilogram meter per second squared. When you take a kilogram times a meter divided by second squared, that is equal to 1 Newton. So newtons are the unit of force that we're going to be using. Let's look at our first example problem of this chapter. We want to know what force, net force, is going to be required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters. So let's write down what we know. We know that the initial velocity, so v0, the initial velocity of the car is 100 kilometers per hour. And the final velocity is going to be 0. It's going to come to a complete stop. And we want it to stop in a delta x, or x minus x naught. We want that distance to be 55 meters. Okay, and it's going to be accelerating at a constant rate. And so what we need to do is we need to refer back to a previous chapter, chapter 2, I believe, where we had those 4 constant acceleration equations. So I've created this formula sheet, and it's on Blackboard. I think you should have this with you at all times, especially when working on homework, so that you can refer back to it. We need to refer back to these constant acceleration questions. We've got, if we look at what we've got, initial velocity, final velocity, delta x. What we want to find out, what we're looking for, is acceleration. So acceleration is what? If we look at this, time, we don't know time, so that kind of rules out that one, and that one. That one's not very helpful. So it's this equation right here, v squared equals v naught squared plus 2a times x minus x naught. That's the one we're going to want to use. So I'll write that out. V squared equals v naught squared plus 2a times x minus x naught. And then subbing in what we know, final velocity is 0. Initial velocity was 100 kilometers per hour squared. Oh, that could be an issue right there. We've got kilometers per hour instead of meters per second. So as I look down at the timer, I see I'm almost up with my 15 minutes. So I'm going to pause right there. I'm going to hold that thought. We'll come back in the next video, and we'll convert this kilometers per hour to meters per second, and then finish solving this problem.